We'll be starting chapter 4 today, which is over exponential and logarithmic functions. So 4.1 is specifically on the exponential functions. We're going to first evaluate exponential functions, graph exponential functions, evaluate functions with base e, and use compound interest formulas. So here's the definition of an exponential function. So you can see that b is the base and x is the exponent. And b has to be a positive constant other than 1, and b has to be greater than 0 but not equal to 1. So x can be any real number. So here's an exponential function. It says 42.2 times 1.56 to the x power models the average amount spent, f of x, in dollars. So this is amount spent in dollars at a shopping mall after X amount of hours. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? So we're going to substitute 3 in for the X because it says that X is hours, and this was 3 hours, so that's what we're going to plug in for our X. So you can see here they substitute a 3. Now you have to make sure you do your order of operations, PEMDAS, so that you do the exponent first. So you have to do the exponents before you do the multiplication. So you would do 1.56 to the third in your calculator, then take that times 42.2, and you get about 160. So after 3 hours at a shopping mall, the average amount spent is $160. Okay, now we'll work on graphing. So your first step is going to be making a table of coordinates. So you can see here that I chose some negatives and then 0 and a positive number. You could use other numbers as well, but you want to have some negatives and positives just to see the pattern that's happening on both sides of the axis. So if I replace this x with -2, 3 to the -2 means the reciprocal of 3 squared. So 3 squared is 9. So 3 to the -2 means do the reciprocal of that. So that's where we get 1/9. It pretty much pushes the 3 to the squared to the bottom. Same here, 3 to the first would have been 3. So 3 to the -1 is the reciprocal, 1/3. Anything to the 0 power is the number 1. And then 3 to the first just means you have 1 3, which is 3. And then you can see those 4 points are plotted on that graph. So then once you have the 4 points or more, you plot them, connect them with a smooth, continuous curve, putting arrows on both ends. So this one says graph 1/2 to the x, which is the same as 2 to the -x. So let's see where that comes from. So if we have 1/2 to the x, we just said 1/2 is the same as 2 to the -1 because it's the reciprocal of 2 to the first. So that would also mean if you multiply these together, that's the same as 2 to the -x. So we're changing it just because it's going to be easier when we do our table if we use the 2 to the -x than the 1/2 to the x. So if I do, let's go ahead and replace, we have 2 to the -x, but we're going to replace x with -2. So you end up with 2 to the -2, which is 2 to the +2, which is 4. So I'll go ahead and plot that point. So -2, 4, be right here. Okay, 2 to the -x, but this time I'm going to put a -1 in. So that's 2 to the +1, which is just 2. So -1, 2 is my next point. Okay, 2 to the negative 0 is just going to be 2 to the 0. We said anything to the 0 power is 1. So 0, 1. Then 2 to the negative x, let's replace the x with a 1. So this one does stay negative. So 2 to the negative 1, we said, is the same as the reciprocal, 1 over 2 to the 1, or 1 over 2. So at 1, we would have a point of 1/2. And 2 to the negative x, but this time replace it with a 2. So that's 2 to the negative 2, which is the reciprocal, 1 over 2 to the 2, or 1/4. So this coordinate is 2 and 1/4. So you can see I'm getting closer and closer to that y-axis. So the graph approaches but never touches the positive side of the x-axis. The x-axis, y equals 0, is the same thing as the x-axis is going to be a horizontal asymptote because it's going to keep approaching it, but it's never going to touch it. So it's going to stay right above there. And just another side note, the graph of g to x equals 1/2 x is the reflection of this positive 2 to the x over the y-axis. So a reflection over the y-axis, you have 1/2 as the base, and then 2 is the other base, and those are reflections of each other. So now that we've graphed some of these, there's some characteristics we're going to be noticing. So the first is that the domain of f of x equals b of x, that's the exponential function, consists of all real numbers from negative infinity to positive infinity. So it just keeps going in the negative or positive direction. So all positive real numbers. Then the range, again, I'm not in the negatives at all. I'm staying above for my y's. So my y's are positives, which means my range are positives. So that's where we get the range consists of all positive real numbers from 0 to infinity. So the domain, the x's, goes from negative infinity to positive infinity, but the range starts at 0. Now if we end up adding or subtracting some things on our equation, then this can change, but just with the regular, without any numbers added or subtracted at the end, we have this as our domain and range. The number 2, the graphs of all exponential functions in this form pass through the point 0, 1. So you can see they all pass through 0, 1. So these are all 4 different exponential equations. Nothing added or subtracted yet. And that's because f of 0, you would replace the b with 0 and get 1. So the y-intercept is always going to be 1. And there is no x-intercept because it never touches the x-axis. If b is greater than 1, this has a graph that goes up to the right and is an increasing function. The greater the value of b, the steeper the increase. So if we compare, let's look at the ones that are greater than 1. We mark those in red. We have this one and this one. So you can see they're both going up to the right. That's where they're increasing. And the 7 one is even steeper because the greater the value of b, the steeper it is. Okay, now if 0 is less than b, but b is less than 1, so b is in between 0 and 1, we mark that. It has a graph that goes down to the right and is decreasing. The smaller the value, the steeper the increase. So let's compare this one and this one. So you can see that they're going down to the right instead of up. And then 3/4 is bigger than 1/2. So the 1/2 is smaller, and so it's a steeper decrease than the 3/4. Okay, number 5. Using that, it's a 1-to-1 and has an inverse that is a function. So we'll look at inverse later. And then number 6, the graph approaches but does not touch the x-axis. The x-axis, which is y = 0, is a horizontal asymptote. So that's where they get this piece of information here. Okay, now here's transformations. We have done these with parabolas and other functions before. This is specifically for exponential functions. So it's going to move vertically if you add or subtract something at the very end. So it's going to shift it up. If you add, it's going to shift it down if you subtract. Then horizontal, that would mean left or right. You can see that it's added to the exponent and subtracted from the exponent. So if it's added in the exponent, it's kind of like when we had something like this in parentheses. Back in other ones, this one moved forward or right 3. So this is similar. So if it's subtraction, you're going to be going to the right. If it's addition, you're going to be going to the left. So it's because it's kind of like a grouping symbol up in the exponent. Okay, then a reflection. If it's the opposite b of x, that reflects the graph about the x-axis. If the exponent is opposite, it goes about the y-axis for a reflection. Then stretching or shrinking vertically. So this one, the c is out front. So you'll vertically stretch it if the c is greater than 1. You'll shrink it if the c is less than 1, in between 0 and 1. And then if the c is in the exponent, that's going to horizontally shrink if c is greater than 1, and it's going to horizontally stretch if it's between 0 and 1. Which you could always find by making a table, but it's also nice to have this to know if your numbers are coming out correctly. Okay, so let's use this graph, f of x equals 3 to the x, to try to figure out what the graph of 3 to the x plus 1 is going to look like. So we're going to start with this, and we're going to make a table of coordinates for that. So that's why we put this right here. So we chose some negatives and positives and 0. So you can see the coordinates, -2, 1/9, -1, 1/3, and so on. So that's the dots that we have plotted. So this is the graph, and we identify 3 points. And we know since there's nothing added or subtracted on this original one, that this is going to be the horizontal asymptote. It's going to be approaching that x-axis. Okay, so now that we've done the 3 to the x, now let's see what would 3 to the x plus 1 look like. So here was our 3 to the x. So if we have x plus 1 as the exponent, this is going to shift f 1 unit to the left. So again, you kind of think opposite, it's plus 1, but that actually means you go backwards or left. So the way you can go backwards 1 is to subtract 1 from x, since you're moving on the x-axis. So that's where they get subtract 1 from each x coordinate. So you can see all they did was the dot was here. They moved it backwards 1. So they did that with every point. So instead of being here at 0, 1, you have to go backwards, and you end up with this coordinate. Okay, and you didn't go up or down, so the horizontal asymptote is still the y = 0 or the x-axis. Okay, let's try another one. So this one is to 2 to the x. So again, we do a table of values to see what the original looks like. It should cross through 0, 1, and then your other points, and it should be going upward to the right because it is greater, the b is greater than 1, so it's going upward to the right. And again, the horizontal asymptote for now is y equals 0. Now we're going to see what is this graph going to look like with a -3 at the end. So here was this graph. Now if we subtract 3, we're going to subtract 3 from the y because we have to shift it 3 units down. So you can see we started at 0, 1. That's where our graph did go, and now we're going to go 1, 2, 3 down. So it ends up being here. And then we did that with this coordinate too. It was right here. You shift it down 3. So now this actually changes the horizontal asymptote. It moves down. So now it's approaching this line here, which is where y equals -3. Okay, now we'll talk about the natural base e. The number e is defined as this value, 1 plus 1 over n to the n. It approaches as n gets larger and larger. So as n approaches infinity, they found that the approximate value of e to 9 decimal places is this. So it's kind of like the number pi. A lot of mathematicians did a lot of experimenting, trial and error, and found that e is always going to be this number. So this is an irrational number because it would keep going. They just round it off. So it's approximately 2.72, and it's called natural base. The function f of x equals e to the x is called the natural exponential function. And we're going to see that the number e, it lies between 2 and 3 because we said it's 2.72. So then if you do 2 squared, you get 4. They found the e squared. You could plug this in your calculator. You should have an e button on your calculator you could play around with. You get about 7.389, and 3 squared is 9. So you can see that the purple graph here lies in between the graph of 2 to the x and 3 to the x because e is about 2.72 to the x. Okay, so let's go ahead and try to solve something with base e. So you're going to want to be able to find this on your calculator. If you can't find it, please reach out to me and I can try to look at your calculator with a picture or something. The exponential function f of x equals 1,145 times e to the 0.0325x. So a long population equation. This is the gray wolf population of the western Great Lakes. X years after 1978. So that's going to be really important. Project the gray wolf's population in the recovery area in 2017. Okay, so first we need to figure out how many X years occurred between 2017 and 1978. So that would be 39 years if you subtract them. So that is going to be what we use for X, since we said X represented years after 1978. So then again, make sure you have to do this first, and within the exponent, you'd have to multiply these two together. They have to stay as one unit. So e to whatever that number is, then multiply by 1,145, and you get about 4,067. So I would try this on your calculator. Make sure you can get this number so that you know what order you had to put your numbers in correctly into your calculator. So this means that the gray wolf population in the western Great Lakes in the year 2017 is projected to be approximately 4,067 wolves. So they use exponential functions a lot with populations to predict maybe rabbit populations or other animals, because you know how rabbits, they just keep increasing really fast. Once there's more and more rabbits, then it just shoots up. So that's an exponential function. Okay, we're going to end by talking about compound interest. So after t years, so this is time, which I have indicated down here. The balance A in an account with principal P and annual interest rate R in decimal form is given by these formulas. So if there's n amount of compounding periods, so let's say it compounds quarterly, n would equal 4 because it's 4 times per year. Annually just means 1. You say biannually or twice a year, that means n equals 2 times a year. Monthly, n would equal 12 times a year. Then continuous compounding means it's compounding constantly. It's P times e to the RT. So first you have to decide which equation you need to use depending on the situation, and then you can just substitute your numbers in. So a sum of 10,000, that's your starting principal, is invested at an annual rate of 8%. So we said the rate has to be in decimal form, so you have to put 0.08 for R. Find the balance in the account after 5 years. So that is T, subject to quarterly compounding. So that means that n equals 4. Okay, so then you just go in and replace the letters with what we said. So we said the P was 10,000. We said the R was 0.08. We said the N was 4, which is also here. And we said the T was 5. And then make sure you follow your order of operations. Do your parentheses first. So you have to do what's in here. Whatever you get for that, you multiply it, or you take it to the exponent, which is going to be 20 here. 4 times 5 is 20. And then you can multiply by your 10,000. So I would try again in your calculator. Make sure you can come up with this number. So that means after 5 years with quarterly compounding, you get $14,859.47 in your account. So you start with 10,000. So after 5 years, I would say that's pretty good. You gained almost $5,000 in 5 years. Okay, so this time let's try the continuous compounding and see what we get. So that's this formula. So the P is still 10,000. The rate is still 0.08. And 5 years is the T, the time. So multiply your exponents together. You have to take e to that power. And then multiply it by 10,000. You get $14,918.25. So this is a better investment option compared to the previous one. The previous one was $14,859.47. So you may have some questions asked which one is better. You just have to solve them both and then compare them.